In this video, we'll go over the concept of limiting reactants and a few calculations that are related to this concept. So, the reality is that both reactants in a chemical reaction are usually not present in limitless amounts. So, one reactant is going to limit the amount of chemical reaction that can occur, the amount of product that can be produced. So if you just look at this schematic that's on the bottom of this slide, you can see what the limiting reactant is. So here are the reactants on the right-hand side of this arrow. And you've got two reactants. You've got the diatomic molecule that's made up of these two larger green spheres, and then some other diatomic molecule made up of these two smaller white spheres. And then you can see the products over here on the right-hand side of the arrow. And what you can see is you've got this new product that forms. It's one green sphere with three of the white spheres around it. But then you've still got some of this diatomic green molecule left over from the reactant side that did not react. So what that tells you, because there's some of this left over, and all of the smaller white diatomic molecule is all used up, that tells you that this white smaller molecule is the limiting reactant. It's the one that's used up first. There are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 of those white atoms on the reactant side, on the left-hand side of the equation, and you can see that all of them become part of the product on the right-hand side. So you can tally them up and you'll see that there are 12 of them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So because all the original of those diatomic molecules are gone and they become part of the product, they're used up first. They're the limiting reactant. So just a little bit of a visual there before we start really getting into the calculations. So here's the first example of how to calculate which of a variety of reactants in a given problem is the limiting reactant. So this problem is focused on what limits algal growth. So this is a picture of algae forming on a pond, and you see this more and more in the summertime because temperatures are higher, but also because nutrients are being added to lakes. And this is a picture from the Puget Sound. This is happening on the Puget Sound. And what's happening is nutrients like phosphorus and nitrogen are being added in excess. So phosphorus and nitrogen, it can come from septic tanks, so sewage leaking out of septic tanks through the soil and groundwater into the Puget Sound. It comes from, in smaller ponds, goose poop, basically, and dog feces when people leave their pet waste. Another big source is fertilizer that people put on their lawns. So when all of these excess nutrients are added, you get these really intense algae blooms. So a lot of algae in the water, and that can lead to really low oxygen conditions. So what this problem is looking at is contamination of a pond with a source of phosphorus, H3PO4. So what the problem says is that 10 grams of H3PO4 contaminate a pond already containing 300 grams of KNO3. So there's the source of, not potassium, of nitrogen. So algae need both nitrogen and phosphorus to produce or to grow. And they grow according to this chemical equation below. So this is an equation that ecologists use. This giant, what looks like a molecule but actually isn't, it is a representation for algae. It's the chemical formula for algae. And it's not a single molecule, but it's just the overall average chemical composition of algae. So they have roughly this ratio of 106 carbons in their biomass to 263 hydrogens to 110 oxygens and so on. So that's the ratio of those 5 different elements in your average algae. So the way that this forms is you have CO2 present in excess, meaning unlimited quantities in terms of this problem. In the air, you have water being one of the reactants, so that's also present in excess because it's part of the pond water. There's a ton of it. The hydrogen plus, or the proton, is also present in excess. But what's potentially limiting is the amount of potassium nitrate or the amount of phosphoric acid. So this problem tells you have 10 grams of phosphoric acid added or contaminating a pond that already contains 300 grams of KNO3. So what you're trying to determine is, of these two, the KNO3 or the H3PO4, which one is the limiting reactant? So the best way to do that, and we're looking at which one limits algal growth. So we're focused on the amount of algae that's produced. So what you can do is you can take the amount of H3PO4 and figure out how much algae that would produce, 10 grams of H3PO4, and then you can take the amount of potassium nitrate that's actually present, which is the 300 grams, see how much algal biomass that actually produces, and whichever of them produces less is the limiting reactant, because it's going to run out first. That's going to limit how much biomass can be produced. So I'm just going to take these two masses and determine how much algal biomass could be produced by each, assuming that the other is unlimited. So if you have 10 grams of H3PO4 and you want to figure out how much of this algal biomass is produced, you first have to convert to moles. So there are 97.994 grams of H3PO4 in 1 mole of H3PO4, so just using the molar mass. And then you use this balanced chemical equation to relate the amount of H3PO4 that reacts to the amount of algal biomass that's produced. So it's a 1-to-1 ratio here. So for every 1 mole of H3PO4 that reacts, you get 1 mole, and I'm just going to say algae instead of writing out this whole huge chemical formula, but that's what I'm referring to. 1 mole of that whole chemical formula is produced. So moles of H3PO4 cancel, grams of H3PO4 cancel, and you're left with 0.102 moles of algae. So now you're going to do the same thing for the amount of KNO3 you have. So you have 300 grams of KNO3, and you're going to assume that the amount of H3PO4 is unlimited, just like the amount of CO2, water, and H plus is unlimited for the purpose of this problem, and see how much algae you could produce with that amount of KNO3. So you're going to do the same exact kind of thing. You've got the molar mass of KNO3 being 101.11 grams for every 1 mole of KNO3. And then you look at how much KNO3 reacts to produce 1 mole of that algal biomass. So you've got 16. So in this case, the ratio is 16 moles of KNO3 react for every 1 mole of algae produced. And again, the word algae is representing that giant chemical formula. I'm just not writing it out. So what you're left with here is moles of KNO3 cancel, grams of KNO3 cancel, and you're left with 0.185 moles of algae. So what you can do now is compare these two numbers. So the number of moles of algae produced by the 10 grams of H3PO4, assuming the amount of KNO3 is unlimited, is less than the amount of algae produced by those 300 grams of KNO3, assuming the H3PO4 was unlimited. So because there's less produced by the H3PO4, that means that H3PO4 is your limiting reactant. the production of algae biomass is going to stop when those 10 grams of H3PO4 run out. That's what it means to be the limiting reactant. So what I just basically did was I determined the theoretical yield of algal biomass that could be produced if I had 10 grams of H3PO4. So in general, the theoretical yield is the amount of product that can be produced, can possibly be produced in theory, in a chemical reaction based on the amount of reactant and the balanced chemical equation. So you're determining theoretical yield using stoichiometry calculations. Contrast that with actual yield. So actual yield is just what it sounds like. It's the actual amount of product produced, that's actually produced during a chemical reaction, during a biological reaction. And it's experimentally determined. It's something that's measured or measured in the field. So it's not something that's calculated based on stoichiometry. It's something that's measured. So just the main points here: theoretical yield is calculated, actual yield is measured. You have to remember these two things because when you see word problems related to these two terms, you have to be able to identify what you're dealing with. And then actual yield is always going to be less than the theoretical yield. It can't be the other way around. And the reason, there are a lot of reasons why actual yield ends up being less than theoretical yield. Some of them are that a small amount of product can be lost to other reactions occurring, or it can be lost during collection of the product of interest in the field or in the laboratory. It can be that reactants are taking part in what are called secondary side reactions, not the reaction that you're studying, but reactions that are actually occurring, so that the reactants are not going into the products of the reaction you're studying. They're becoming products of some other reaction that you're not considering and that you're not measuring. And then there are just inherent limitations of laboratory equipment. So there are a lot of reasons why the actual yield is less than the theoretical yield, but it's always less. And then once you have these two terms, you can calculate something called the percent yield. So notice that the percent yield, it has that measured actual yield in the numerator, and then you've got your calculated theoretical yield in the denominator. And I want to emphasize that the theoretical yield, it has to be calculated based on the limiting reactant. So you have to first determine what is the limiting reactant, and then you have to calculate the amount of product obtained from the stoichiometry of the balanced chemical equation based on the amount of limiting reactant you have. You can't use the reactant that's not limiting, because if you do that, it's going to give you an artificially high amount of some product produced. You have to use the limiting reactant because the reaction is going to stop when the limiting reactant is used up, and therefore no more of this product will be produced. So make sure you're always using the limiting reactant for your theoretical yield calculations. So here's an example of percent yield. This problem says a researcher estimates algal biomass in the pond, which was that pond contaminated with 10 grams of H3PO4 and already containing 300 grams of KNO3, to be 314.6 grams. So what happens is that a researcher goes out and measures the algae biomass. So here are algae, what they look like under a microscope. And people can actually go out and measure them using these nets. They put these nets, they drag it behind a boat, they collect a bunch of biomass, and they can estimate, doing that, the amount of algal biomass in a lake. So that's what this measured number is. It's for this lake that was contaminated with the 10 grams of H3PO4 and that already had the 300 grams of KNO3. So this amount of algal biomass was produced due to these amounts of H3PO4 and KNO3. So then this question is asking, I meant to rewrite this question. I copied it from the other slide. What I wanted to ask here is, what is the percent yield of algal biomass? So in order to determine the percent yield, you need to first know the theoretical yield. This 314.6 number is the actual yield. So that's the numerator of your percent yield calculation. But you need to find the theoretical yield. So you'll remember from the first version of this problem, the H3PO4 was determined to be the limiting reactant. So we're going to use those 10 grams of H3PO4 to determine how much of this algal biomass could possibly be produced. And if you remember from that other problem, I'm just going to flip back a few slides here. We determined that those 10 grams of H3PO4 would result in 0.012 moles of algae. So I'm going to start with this 0.102 moles of algae so I don't have to do all of these steps again. Okay, so here we go. We've got the 0.102 moles of algae resulting from that 10 grams of H3PO4. And again, when I write algae, I'm referring to this entire chemical formula, all of that. So when I convert to grams, you have to convert moles of this chemical formula, which is representing the algae biomass, to grams, because when you calculate percent yield, it has to be, the theoretical yield has to be in the same units as the measured or the actual yield, that 314.6 grams. So I'm going to get my theoretical yield for algal biomass also into grams. And I do that by using the molar mass of this giant chemical formula, which turns out to be 3,553.259. This is grams of algae per 1 mole of algae. And what you end up with, moles of algae cancel, and you have 362.43 grams of algae. So the last part here, and this is your theoretical yield. In theory, this is how much algal biomass, this guy, could be produced from 10 grams of H3PO4, which was your limiting reactant. So now, to calculate percent yield, you're going to just put the actual yield over the theoretical yield and multiply by 100. So again, the actual yield is this 314.6 number that you were given. That's how much was actually collected by the researcher and actually measured in the lake or the pond by the researcher. And then this 362.43 is how much algal biomass could be produced in theory based on that amount of H3PO4, those 10 grams of H3PO4. And the final answer here for percent yield is 86.8%. So that is percent yield. The last thing we're going to look at in the limiting reactant section is what's called reactant in excess. You can think of the reactant in excess as the leftovers. So this is the reactant, or these are the reactants, there can be more than one of them, that are not limiting. And it's because they occur in a quantity greater than what is needed or required to completely react with the limiting reactant. So the limiting reactant gets all used up and it's gone, the reaction stops, but there's still some of these reactants in excess left over. And I already mentioned there can be more than one if there are more than 2 reactants. So it's possible to calculate the amounts or the quantities of reactant in excess remaining after the limiting reactant is used up. So all you do is you take the amount of that reactant in excess initially available and subtract out the amount that was reacted. Another way to think about this before we get to the calculation part, if you were going to make some hot dogs and buns to eat, and you had 5 hot dogs and you had 4 buns, you could only make 4 of these. So the 4 hot dogs would be your theoretical yield, and the buns would be your limiting reactant, because they're limiting how many of these hot dogs in buns you could make. And what's left over is one hot dog, so that's your reactant in excess, also known as the excess reagent. When we're looking at this problem, what's left over is some of the KNO3, because we already know that the H3PO4 is the limiting reactant. That gets all used up. So what we want to do is determine how much of this KNO3 is left over. And here's the problem. How much of the 300 grams of KNO3 remains when all of the 10 grams of H3PO4 are used up? So what you want to do is you want to take your limiting reactant, which in this case is the 10 grams of H3PO4, and you want to find out how much KNO3 reacts with that amount of limiting reactant. So you first want to convert the grams of H3PO4 to moles so that you can do that mole to mole comparison between H3PO4 and KNO3. So you use the molar mass. And then you look at the reaction stoichiometry, those stoichiometric coefficients, and say for every 1 mole of H3PO4 that reacts, I get 16 moles of KNO3 reacting. So you're almost there. You've got moles of H3PO4 canceling out, grams of H3PO4 canceling out. You want to be able to subtract the amount of KNO3 used up from the initial amount. And the initial amount is in grams, so you're going to want the amount of KNO3 that was actually used up in the reaction to be in grams too. So to do that, you just go from moles of KNO3 to grams of KNO3 using the molar mass of KNO3, which is 101.11 grams. So now moles of KNO3 cancel, and you're left with 165, which is 200 grams of KNO3. And I'm rounding up from 165 to 200, because if you look at the sig figs of these two numbers, you got one sig fig in the KNO3 and one here. So I've only got one sig fig in my answer. So this is the amount of KNO3 that is used up in the reaction. So you started with 300 grams of KNO3 and you used up 200 grams of KNO3. So what you've got left over after the reaction stops, after the production of that biomass stops, is 100 grams of KNO3.